Professor Sheila Widnall. We're really lucky that she's able to come and talk to us today. She's been here at MIT since 1964 as a professor and then as provost, but she didn't serve very long as provost because she was assigned to go to Washington by the president to be the Secretary of the Air Force, which she did for almost 5 years, I guess.
4 years.
4 years.
4 years and a bit.
Then came back here, and she's now an institute professor, which basically means you can do anything you want, right? Including come and talk to our class. In particular, Professor Widnall was on the Columbia Accident Investigation Board, and that specifically is what she's going to talk to us about today, along with just general comments about how this relates back to systems engineering, the design, operation of the shuttle, and basically anything else that you would like to say, because it's your time. So thanks for being with us, Sheila.
Okay, well, thank you, Jeff. As I understand the schedule, it's 2 hours, and if I don't finish, we still take a break.
And
then we come back and finish.
And generally,
right?
the way we've run the classes is that we encourage students to ask questions while you're
Absolutely.
talking.
So that'll probably slow me down a bit. So anyway,
up to you.
2 hours, we'll just take it as it comes.
Yeah.
Okay, well, I am going to focus on the Columbia accident investigation. I must say, and I'm sure I'll say this many times as I go through it, it was an incredible experience to be a member of that board. So let me go through some of the issues that we talked about. Now, if I can get, where's that little thing? Oh, there it is. Okay.
Columbia has disintegrated in the skies over Texas.
I get chills up my back when I see that. The reason I show this is for two reasons. First of all, I mean, it was, in fact, an incredible event. I'm sure that all of you can remember where you were that morning when that happened. I also show it because of the expression on the face of the principal mission controller, Leroy Kane, when he realized that the shuttle was lost. And if the shuttle doesn't make it to Cape Kennedy more or less on schedule, there's no engine at that point, you got a problem. And so he was in a windowless box in Houston, and so he had no kind of external, although all the citizens of Texas knew what had happened, the guys in the windowless box did not. So it was really an incredible emotional experience for NASA, for all of NASA as an agency. But then what happens after that? Well, fortunately, the Challenger Commission had anticipated the need for a method to call an accident board into being if there should be another shuttle accident. And so there were individuals who were more or less ex officio by rank or title waiting to be called. So the fact of the matter is that on Saturday, when this all happened, the Accident Investigation Board was pretty much called into being at that point. Now, who were the Accident Investigation Board at that point? Well, they were primarily government employees, not so much NASA employees. That clearly would have been unacceptable. But they were military, 3 Air Force generals, the head of Air Force Safety, a general from Space Command, and a general from Materiel Command who had actually served as an executive staff to the Challenger Commission. That would be General Barry. So they had some very good experience. The board was chaired by Admiral Hal Gaiman, who had been the Vice Chief of Naval Operations. He had also been the chairman of the coal investigation. I don't remember how many of you remember the coal investigation, but that was a big explosion in, I don't remember what, it's in the Middle East. I don't remember if it was, where was it? Yemen. Yemen, yeah, it was probably Yemen. Killing 19 people. And there were other government employees, somebody from the National Transportation Safety Board, Jim Halleck, who's across the street here at the Department of Transportation, the head of NASA Ames, and the head of Navy Safety, Admiral Turcotte. So it was a smaller board than it ultimately ended up being, and so that was like February 2nd, which is pretty much the day of the accident. But I think it was fairly clear from the reaction of the public and the media, of course, in particular, standing instead for the public, that this was not acceptable, that you could not have the government investigating itself. So there was a big hue and cry for the addition of public members, and that's basically when I came on board, along with Sally Ride, along with I'm blanking on names because I'm at that sort of age, but we had a Nobel Prize physicist from Stanford. You have to have a Nobel Prize physicist on a shuttle investigation. And also somebody who had been looking into issues of policy and history with respect to the shuttle program. And I'm not getting any of these names right, so I'm not even going to try. Pardon?
The class has met John Logston.
John Logston, right, thank you, John Logston. Doug Osheroff was the Stanford physicist. He was kind of a kick because at the beginning he was very media shy. He just wouldn't talk to the media, but then he really got into it and he went way outside the box, which was kind of interesting to see how that all happened. In any case, we were all pulled together and we were chartered to uncover the facts as well as the actual or probable cause of the shuttle mishap and recommend preventative and other appropriate actions to preclude the recurrence of a similar mishap. Yes?
Before you and Sally Ride came on, there were no females on the
No, that's right, no women.
Do you think that had any effects, or the fact that you came on?
I'm not sure, maybe a little bit, but actually the day of the accident, of course, everybody was saying, what happened? That's not what I was saying. I was saying, I wonder who's going to be on the board. I actually had a strong sense that I, in fact, would be on the board. Think about it. Gene Covert had been on the Challenger, so I think, like you have to have a Nobel Prize physicist from Stanford, you have to have an aeronautical engineer from MIT. I think the other thing was, as Secretary of the Air Force, I was really in charge of accident investigation. All accident investigations reported to me in both, well, you guys don't know a lot about accident investigations in the military, but there are two accident investigations in the military. One called a safety investigation, which is privileged. And you take testimony and you seal it. And I'll talk about that later because we tried to replicate some of that on the Columbia investigation. So you have that one, and then you have the public investigation, which you take testimony, people can be court-martialed, So there's an accident investigation procedure that goes on in the Air Force, and I had really been in charge of that. So in addition to being an aerodynamicist, which is always good, I was the aerodynamicist on the commission. I was, a faculty member at MIT. I'd been Secretary of the Air Force. I'd been in charge of accidents. So also I had spent my last 5 years really being interested in space, safety, mission assurance, and space. So, all these things kind of came together. Sally Ride was obvious. She was an astronaut, and she had been a member of the Challenger Investigation Board, so she brought that historic knowledge. So I don't think that was the primary thing, but it's probably good to have a balanced group. Now, I think there was something, I actually did come on board pretty much February 18th. That was when I came. I think that one of the early issues that we faced was our relationship with NASA. I think at the very beginning, NASA had this image that we would work for them. That was one thing. And the second thing was that we would find, the widget that failed, and then we would leave, leaving them to carry on. Not with this group of people, you don't do that, and not in this situation. We very clearly and fairly early established our independence. We removed a number of senior NASA people from inline responsibility for the investigation, like Ralph Rowe, and I'm blanking on these names, but the people who had been in charge of the program, of course, some of them quit even before we got there. But the people who had been Linda Ham, yeah, Linda Ham. So we removed Ralph Rowe, and yeah, she was right in the middle of things, and we just said, look, we're not questioning your integrity, but you just cannot investigate yourself. So we need to move you aside. You go back to your normal responsibilities and bring in independent people who had not been so deeply involved, and they will be the primary interface between the Accident Investigation Board and NASA, because we really needed to use NASA. I basically had very strong interactions with the NASA Aerodynamics Division, and you'll see the reasons why as we proceed. But at the end of my interaction with them, which occurred at the end of June, and they presented their 450-page report to me with all the calculations and studies and things that they had done at my direction, I basically looked to the group and I said, well, I think I could probably give 22 PhDs at this point to this group, because we had really pressed the envelope in terms of improving the methodology that we used to analyze some of the details of kind of what I'm going to talk about. But in any case, the issue of independence was extremely important, and I recall a lot of meetings with a lot of banging on the table and yelling and screaming before we finally got this all straightened out. Admiral Gaiman was an incredible leader. He really just did such good work. He had a sense of, you know, where to press and where to stand pat, and, you know, how to interact. It really was, he was really a marvelous chairman. Incidentally, he recently served on the BRAC Commission, so he's somebody who's deeply involved in public service. And I know from my conversations with him that he's a person who refuses to serve on any board of directors that has anything to do with the Department of Defense, because he does not want to give the appearance of a conflict of interest. And, you know, he's just a man of incredible integrity. Obviously, I'm a big fan. In any case, we proceeded then to wrap our group together and begin our interactions with NASA. Let me show you, some sense, the fundamental cause of this accident. This is the launch video that was available pretty much the weekend that the accident occurred. This was available. This is a close-up photo of the bipod, and it was this piece of foam that came off the shuttle. And you're going to see a video of this foam coming off, hitting the shuttle here and smashing. And I'll show that a couple times just to you know. And this happened about 81 seconds, 82 seconds after launch. I don't remember the Mach number, but I think it was something like 2.5, something like that. So this is the video, and you see the piece coming off and smashing, and I'll show it again. Okay, so that video was pretty much available the weekend of the launch. So there was an understanding among senior program managers that there could be a problem. Now, what did we know about it? Well, there were video cameras, you know, at the site. There was a video camera located here, video camera located here. A rather shallow angle to try to do any triangulation, but obviously you use what you have, and so as a result of triangulating these two video cameras, we were able to make an estimate.
It's probably also worth mentioning that there were other video cameras,
yeah,
but they were out of order.
Right, and I was going to talk about
okay.
that with respect to our recommendations. One of our recommendations was that you should that working video cameras were an absolute necessity for launch. In other words, you do not launch if you don't have a reasonable set of video cameras, and oh, by the way, you don't launch at night, because then obviously the video cameras wouldn't be any good. So that was one of our recommendations, what I would call a near-term recommendation, return to flight recommendation. Yes?
After the Challenger accident, was there an increase also in video?
You know, I don't know the answer to that. Maybe you know the answer to that. You know, it's very interesting, because I've been doing a lot of mission assurance and space accident stuff. You almost always have a picture of a space accident, mostly because they occur on launch. So in the case of the Challenger, I think we had excellent video. You could see the little hole in the Challenger. You could see the stuff coming out. In this case, we had reasonable video of potential, impact.
You can launch with an 8,000-foot ceiling. In which
I don't
case
know.
we would not have seen the Challenger.
Yeah, at that point. I don't think it's true now, and I know that, I don't know how they followed up on that, but there's also a possibility of using aircraft if they can't get the video. In any case, it turns out to be an important issue, and we made recommendations in that. So what we knew about the impact was we figured. Now let me locate you this. Of course, you guys all know exactly what this is, but this is the left wing underside. This is where the curvature, changes, and so it was kind of right in here someplace. What we refer to as panel 7, panel 8, panel 9 on the underside of the composite material that surrounds the leading edge. Now, I don't know if you guys have studied that composite material. It is a truly marvelous material, and I may say a little bit more about it. So we sort of knew where the impact had occurred. Obviously, we were hampered by this shallow angle of the video, but this was our best estimate. The velocity was estimated to be, roughly 800 feet per second, and that was obtained from several different methods. One was a computational fluid dynamics calculation of, how would the airstream accelerate a piece of foam of that particular shape weighing 2 pounds and having it hit. And the other thing was from the video itself. So we had pretty good correlation between the estimates based on the video and the estimates based on calculations using computational fluid dynamics. So we felt pretty comfortable about this velocity. Okay. What did we know when I joined the board? What did we know? What kind of data did we have? Well, this particular vehicle had some telemetry of some sensors, in the wing and in other places. At this point in the investigation, we had not recovered the flight data recorder. The other thing that's interesting is that this is the only vehicle with a flight data recorder. This is the vehicle that was considered to be a research and development vehicle. All the other vehicles were operational. They didn't equip them with flight data recorders. Now, I'll get back to this point when I talk about the criticisms that we had of the agency, but we took strong exception to the notion that the shuttle had been declared to be operational, and therefore there was no need to continue to study it as a research and development vehicle, that it was just like a Piper Cub or a 747, that a takeoff was a routine event and was not, in fact, a major event. And even in this system, if a sensor failed in the flight data recorder, it was not replaced. So what we had on the Columbia was a wasting asset. But at least we had an asset. We had a flight data recorder. At this point, we had not found it. Where were these sensors located? Well, there were a lot of sensors in the wheel well. There were some temperature sensors in this region of the leading edge. There were some temperature sensors back in here, different places. Now, one thing that's significant about this is that these temperature sensors were connected to 2 different boxes. Actually, it looks like 3, but this box, what I'm going to focus on are these wires. Some of the temperature sensors were connected to wires that were basically in this region and running along the wheel well, and then ultimately, of course, connecting to the sensors. And some of the sensors were connected to this thing, which was back here, and its wire ran along here. Now, why is that important? Because this is the area of impact, and this is the area where the gas entered, and one of the early indications of what had happened were that these wire bundles were cut by the gas that came in the hole. So that's one of the reasons why that was important, and kind of how we began to hypothesize what had gone wrong. Now you see the time was sort of 8:44, so the relevant times, that's Eastern Standard, I think. I was shopping actually at the time. Between 8:44 and 9 o'clock is when all of this took place. So, you know, we're talking about 15 minutes of problems. At 8:44 everything was fine, at 9 o'clock the vehicle had crashed. So this thing happened in about 15 minutes. Okay, so that's what we had. So at 8:52, you began to get some sensors that were lost back here. Well, no, that's kind of strange. There was nothing going on back there. What was happening? Why did these sensors fail first? It's because of the wire that controls these sensors is located here in this sort of critical area. So that was a wire cutting. Yes?
You said that the other orbiters don't have
flight data recorders, right?
Don't nearly all commercial airliners.
Commercial, that's a whole different mindset. Yeah. I mean, those carry people. And, yeah, it's an FAA regulation, flight data recorders. Yeah. I mean, it's a whole philosophy of accident investigation.
On the shuttle, the telemetry is being constantly down.
Telemetries, yeah, but the telemetry, let me try to put that in context. I would say that there are 10 times more sensors in the flight data recorder than in the telemetry. So roughly speaking, you do get data coming down, but it's not as complete as what we had in the flight data recorder. So in any case, this is the story that begins to emerge, that the wires were being cut, and so we could follow, you know, the failure of these sensors right up to the point when the vehicle, we had loss of signal, which was at about 8:59. So this whole thing happened fairly rapidly, of course, and this was the trajectory of the vehicle. I'll show another picture, but the whole problem sort of started off Hawaii, and then you know, the vehicle began to break up here in Texas. So this was kind of what we knew on roughly February 18th. We had this. In fact, that's all we knew, really. I mean, the temperature increases were not particularly dramatic. You know, 50 degrees, 30 degrees. It's not really very interesting. What was interesting is the wires were cut. That was more interesting. Okay, so we began to look for the debris. And we had people essentially marching over the state of Texas, about that far apart. It was an extremely expensive thing, but we recovered about 40% of the material that came from Columbia. And of course, you know, it's all these little pieces of stuff that fell on the ground. Fortunately, it fell in a fairly rural area. Nobody was hurt. I don't think there was any damage to structures or anything like that. And we were able to recover, you know, a great deal of it. A lot of it, because I actually looked at the weather radar, a lot of it was very small particles and actually floated into the Gulf of Mexico. I mean, you could see it on the weather radar, you know, the NEXRAD system. You guys all know what the weather radar is, but you could see the particles streaming into the Gulf of Mexico. So I think a lot of it was just sort of vaporized. And there's a footprint of the debris. And, you know, we did a lot of searching in that area. We tried to search upstream. We were really trying to find the earliest pieces of debris, but these fell down, you know, onesies and twosies in really strange places, like in mountains in Utah and stuff like that. So we were never really successful, although some of these had been tracked on radar by the FAA. Okay, and there is the debris collection hangar down at Kennedy. This is pretty standard stuff for commercial aircraft. I think you all know that when you have an accident, what you try to do is recover the debris and try to reconstruct the vehicle. This debris was particularly interesting, and I don't know if I have a graph later, but let me talk a little bit about the temperatures involved. We're talking about re-entry of a damaged vehicle at Mach 25. Now, of course, that's the course that I tried to get out of when I was a graduate student, was that high temperature stuff where the gas begins to ionize and dissociate and, you know, that enthalpy stuff. You know, I really tried to avoid that, so I get paid back. Anyways, that is the subject of high-speed gas dynamics, and so I had to take a refresher course, and Judd Barron, one of our faculty members, was extremely helpful. He used to go over to his house on Saturdays, and he'd give me references. But roughly speaking, if the gas didn't dissociate, the temperatures on re-entry at the leading edge of this vehicle would be about 50,000 degrees Fahrenheit, which is really pretty hot. The fact that the gas does dissociate, ionization at this Mach number is not that important. It interferes with the radio signals, but it does not, in fact, absorb a lot of energy. The gas is slightly ionized, 1%, something like that, 2%, but not enough to be a big energy issue. But the dissociation of oxygen, dissociation of nitrogen is an extremely important phenomena. And because of that, the gas temperature is roughly 10,000 degrees Fahrenheit, which is a lot better than 50,000 degrees Fahrenheit. So that makes a big difference. But let's talk about the leading edge material. The leading edge material is, in fact, an incredible material. It's a carbon-carbon composite material. It's about 1/4 of an inch thick, and it can withstand a temperature of 3,200 degrees Fahrenheit. And that was what? The shuttle was conceived in, you know, what are we talking about here? 70?
Yeah, 69.
Right.
70.
We don't have much better materials today. You know, we might be able to go to 3,400 degrees Fahrenheit instead of 3,200 degrees Fahrenheit. So, you know, we've made some progress. But this is a marvelous material. Now, how in the world, with a gas temperature of 10,000 degrees Fahrenheit, can you use a material of 3,200 degrees Fahrenheit? Well, that's the other part that I try to avoid as a graduate student. It's called radiation. And what is it? The Stefan Boltzmann law of radiation, T to the 4th. And you can write it down on the back of an envelope and you can calculate it. And it turns out that the gas coming in does heat the leading edge up, but then the leading edge radiates out the right amount of energy to basically have an equilibrium temperature of the order of magnitude of, say, 2,800 degrees or maybe 3,000 degrees. So it's comfortably below its maximum temperature. But this is obviously a very dangerous situation. In the early days of the shuttle program, they made some tests of this material, its ability to withstand impact. They shot BBs at it and made 1/4 inch holes in it. And then I'm a little fuzzy on this part. They may have tested those 1/4 inch holes in an arc jet to see would they ablate, you know, how would they behave, would they grow. And I think at that point they felt comfortable that they could withstand the impact of a BB and not be destroyed. So that's an important set of issues. I guess the other thing I want to point out is if you have a good, solid, continuous leading edge, you can support a temperature of 3,200 degrees because of radiation. But if you get a hole in that leading edge, then the gas that goes into the cavity behind the leading edge is your old friend 10,000 degrees. There is no radiation balance to bring you back down to 3,200 degrees. So you have a 7 to 10,000 degree arc jet coming through any major size hole in the leading edge of the shuttle. And that's, of course, exactly what happened.
Remind people that 10,000 degrees is the surface temperature of the sun.
Oh, it's very hot, yes.
Yeah. There
is no material that will withstand this. And this happens, and this happens routinely in shuttle operations. The shuttle re-enters at Mach 25, and the temperatures of the gas surrounding the shuttle are about 10,000 degrees. And we've successfully gone through how many shuttle flights?
In total?
In total.
114.
114, so it's a sporty course. Okay, now I want to talk about something else we knew before we found the flight data recorder. And this was of great interest to me for lots of different reasons, but One of the things we were able to do is infer the aerodynamics of the damaged vehicle by looking at what the flight control system had to do in order to keep the shuttle perfectly on its pre-assigned flight path. In other words, until very late in the flight, the shuttle was doing exactly what it was programmed to do. But it was working a lot harder and in very off-nominal ways. So let's talk about, and we had to back this out. Now this is almost like a 0/0 calculation, so it's a little sensitive, a little hard to do, but this was something the aerodynamics group did, and you know, I worked really closely with these guys. I have great admiration for them. They were able to back out the off-nominal roll moments and the off-nominal yaw moments of the shuttle during this final reentry. And I made this little schematic of kind of where were they when some of these things happened in terms of the coast of California and, you know, their flight over New Mexico and down to loss of control over Texas. Before I do that, let me just add to my previous remark that you almost always have a picture of a space accident. Now, normally that's because space accidents occur on launch. This is a remarkable photo of a space accident. This photo was taken by, modestly, my guys at Kirtland Air Force Base. And basically, they've been working with optics. That's basically their business. And so, Saturday morning, IBM personal computer, fooling around with some little telescope that, you know, they'd been developing for tracking things. And so they said, well, why don't we just track the shuttle? It's coming in. So why don't we just track the shuttle and see if we can take a picture of it? Well, very interesting. What's interesting about this photo? First of all, that overlay is just a grid that sort of shows you what the shuttle would look like in that configuration. But what is interesting about that photo? What?
Left leading edge looks something.
Yeah, this is interesting. This is a bulge at the leading edge showing some distortion of the shock shape due to vehicle damage. And I obviously consider this photo to be extremely probative. And also there's a small amount of debris that's got some optical signature to it that's sort of streaming out of that general area, indicating, I mean, there's all sorts of things going on in this vehicle, but one of the things that was going on was the melting of aluminum, the vaporization of aluminum, and the combustion of aluminum, because aluminum will burn. I don't know how many of you know it, but aluminum is something you add to rocket engines in order to get higher temperatures. It burns when it gets hot enough. It can be a very dangerous material. In any case, we suspect there was a lot of aluminum combustion going on, while this thing was happening. So this is... Mm-hmm.
Have there been, for reference, any similar photographs?
No!
So we didn't have a nominal baseline?
No, we didn't have a... As far as I know, I actually don't know the answer to that question. I know, because I know the guys who took the photo, and I know their boss, that they were doing it for a very specific reason that had nothing to do with anything they had done in the past. They were trying to develop a little telescope to track things, because that's what they do at Kirtland, is they work with optics. But I don't know whether anybody has tried to do it. I suspect their level of precision is a little greater than, the average citizen trying to take a picture of the shuttle coming in. And they had... But this was not a really high-powered telescope. I mean, they had some really high-powered telescopes at Kirtland. This was just, it's a small one. Anyway, I don't know the answer to that.
That was just normal light. There wasn't IR.
Well, I think what we're looking at here is the glowing of this 10,000-degree envelope that surrounds the shuttle. So that's what we're looking at, is we're looking at the radiation, basically, from the gas surrounding the shuttle.
Yeah, I mean, but it was normal film.
Yeah, it was normal. Now, of course, this was 8:50 in the morning Boston time, so it was dark. This is February, so it probably was dark in New Mexico. Okay, so that's kind of the picture that we got, which I think is really neat. This is the trajectory. But this is the backing out of the off-nominal moments. Now let me talk about the yaw moment, just to give you a feeling for, what does all this mean. So I contend that off-nominal aerodynamic forces are an indication of external damage to the vehicle. That's basically what it is. The vehicle was flying because its reaction jets were, moving and doing all sorts of things. The aerodynamic surfaces were virtually useless at these dynamic pressures. So this was a reaction jet controlled vehicle, but we knew how much force the reaction jets were putting out, so we could do the vehicle aerodynamics. Let me talk about the yaw moment. So what we have here is that as the accident began, the yaw moment became negative, kind of flattened out for a little while, and then became very strongly negative. Okay, what's yaw moment? Yaw moment is the force turning the vehicle this way. So if I have a damaged left wing, what's my yaw moment going to be, and why? Well, I'm going to have increased drag on this wing because I've got a big chunk out of the leading edge. I've got a disturbed shock. I've got all sorts of stagnation pressure in this region where in normal circumstances it would be smoothly flowing. So I've got increased drag on this wing, and so that's going to drive me this way, which is exactly what you see. That's off-nominal yaw moment. Roll moment's a little stranger. The roll moment, basically, as the drag increases, and you probably lose lift, so your roll moment begins to go like that. So you have decreasing roll moment. This was a bit of a mystery, and because basically what it said is you lose roll moment, but then all of a sudden your roll moment increases. That's a problem that only an aeroelastician could solve. I happen to be an aeroelastician. Do you know what I'm talking about? If you stick your hand out of the car window and you turn it slightly, what happens? It goes up, and it may also turn some more. In other words, if you lose the leading edge spar of a wing, you lose its resistance to torsion. Now, we don't have all the data we need to prove that that's what was going on, but I believe, a strong hypothesis that we lost the strength in the leading edge spar, and the leading edge spar tipped up, and obviously the lift would increase because the angle of attack was increasing. But this was a very, very puzzling and very interesting phenomena. But in any case, what happened is that both the roll moments and the yaw moments got too strong for the control system of the vehicle, which again was just the reaction control jets that are on the vertical area around the vertical tail. So then ultimately the thing went into a spin, lost control, and then of course the vehicle was lost, began to break apart. So this was a very interesting set of data. And as I say, when we started, this was pretty much all we had. There was a pivotal moment, and then it occurred sort of at the end of March, about March 27th. Remember, the accident occurred February 1st, where we found the flight data recorder. And we found it by these guys walking across the field looking for stuff. And the flight data recorder was found, and it was in pretty good condition, considering it had done a re-entry at Mach 25. So we were able to recover. I don't believe any of the data from the flight data recorder was lost. I think we pretty much got it all. And so at that point, we had hundreds and hundreds of data points. And I would say, at this point, I would say NASA's attitude changed at this point. I think up to this point, there had been a certain level of denial about the accident, about what caused it. You know, maybe it was a micrometeorite, maybe it was some unexplained, system failure that they were not really sure that we were pursuing the right road until the flight data recorder was found. And I think maybe that's to NASA's credit. NASA's data-driven. And when they began to see the data, and they began to see how well the data correlated with the hypothesis and the models, then they hopped right on board and did a tremendous amount of work to try to help us unscramble all of this and come to a hypothesis. Okay, what kind of data did we have? Well, this is a picture of the leading edge spar, this big thing here. And this is a picture of the hypothesis, sort of about a piece of foam taking out a fairly large piece of this carbon-carbon fiber and allowing hot gas to enter into the region behind the leading edge. This leading edge region is, as you can see by the picture, is sort of hollow. There isn't anything back there. There is a layer of insulation covering this, but that is because of the radiation. In other words, because this in fact is 3,200 degrees, it radiates in both directions, and so there's a layer of insulation here to protect against radiation, but that insulation will not protect against the equivalent of an arc jet that's just, burrowing and blasting it. So it was fairly quickly that this gas just blew a hole through the leading edge spar. And how did we know that? Well, it's kind of interesting. Let's look at one of these. We had all these wires back here, and we had these temperature sensors, and let's just pick one temperature sensor. I don't even know where it was located, but it was not located in this region. It was located back someplace else. So we looked at the temperature sensor and compared it with earlier flights, where the earlier flights would show this behavior, and this temperature sensor kind of did this. It began to go up, and then all of a sudden, we lost it. What happened? What? The wire was cut. The wire was cut. See, this cutting wires thing turns out to be really important. We got more information from that than we did from the actual temperatures. But in any case, the wire was cut, and in fact, we know exactly when all of the wires were cut. Well, all the wires cut imply an 18-degree diameter, an 18-inch diameter hole in leading edge spar, because if all the wires are gone, that means there's a really big hole here. And it happens fairly quickly. As you can see, we have the time pretty well nailed. It happened in about a minute. It took a minute once the hot gas began to penetrate through the leading edge spar for the gas to, make a very large hole in the leading edge spar, which of course is the principal structural member of the wing. Okay, so the picture begins to emerge of wire bundles being cut, of gas entering here, of this wire bundle being cut to the sensor, of this, in fact, entire region beginning to sort of fill up with extremely hot gas, 7,000 degrees roughly, eventually entering the wheel well, although that was later in the flight. We did have some indication of the gas in the wheel well because of the temperatures and the loss of sensors. Okay. So because of this, the focus turned to the question of this, what we call RCC, which is this composite material that surrounds the leading edge, and where did we find it? And we found a lot of it. I mean, we found it all along in Texas. The other thing we were able to look at with respect to the RCC is its pattern of erosion. I mean, this RCC was kind of flopping out in the breeze here at roughly 7,000 to 10,000 degrees. And so it was a material that was being effectively subject to an arc jet. And if you took a material like that and stuck it in an arc jet, it probably would ablate, and it would maybe sharpen up, and you'd have maybe little pointy edges where it had ablated. And so we looked at the part that was particularly eroded, and that would be the yellow stuff, and we found that upstream of the stuff that was more put together, the rest of the RCC from the wing, and from the right wing, we found the right wing downstream of the left wing, which means that the left wing came off first. Now, the image that emerges from this is hole in the leading edge, material coming off, but gas flow going down this, what some people call the channel. I never liked that term, but it's a big open cavity. gas flowing down this open cavity and simply destroying all the fittings that held the RCC onto the wing. I mean, you know, the screws and the brackets and all of that. And the wing, again, the gas is coming in, and the wing just unzips. All this stuff just kind of unzips and falls off. And of course, that's, you know, that's where we find it. It's just lying on the ground. It all unzipped and fell off. Okay, what did we actually find? I only show the part that's of interest. We found the RCC. This is kind of typical of what we found. We found a fair amount of it. Some pieces we found pretty much all of it. If you look at RCC panel number 5, we pretty much found all of it. And we found a fair amount of the upper part. We think that the breach was here. We think that this was maybe the part that unzipped, the part that was downstream. But we saw a lot of it. Okay, so what we had to do, however, is to construct analysis using a whole lot of different disciplines, and we had to be able to analyze according to the rules of that discipline and line them all up for consistency. And I would say that we never found a theoretical or experimental result that was in conflict with our basic hypothesis, and that everything sort of lined up. I was more or less in charge of the aerodynamic analysis, as well as my favorite subject, thermodynamic analysis. I never liked that part either. But, you know, the whole question of heat transfer and how fast these materials would melt. So I was pretty much involved in that. I may have another picture later, but let me just show you some pictures that we had. There's a hypersonic wind tunnel down at Langley, and we did a lot of tests in that wind tunnel. One of the things we did is we had a score of wind tunnel models. They were about this big. But we took chunks out of their leading edge. You know, we'd have a wind tunnel model, which was the nominal shuttle, and then we'd have a nominal shuttle with panel 6 missing. Then a nominal shuttle with panel 7 missing. And a nominal shuttle with panel 8 missing. And so we did all of these tests. And then we did tests with a hole in the middle of the wing and, you know, almost any geometry you could think of, and got a whole series of pictures like this. Now, what this picture refers to is that there's a coating that you can put on a wind tunnel model that shows you what the temperature is. And it turns, you know, different colors for different temperatures. Looking at this model, I'm assuming, well, there's a little bit of red here, so that's probably the high temperature. And there's probably a little yellow here, that's probably a little lower than the red. And then you see the green, that's probably a little intermediate temperature. And then you see the blue, that's probably lower. But if you look at this, you can, being an aerodynamicist, I can tell you where that vehicle gets hot. It gets hot near stagnation points and near leading edges, and especially at the stagnation point on the vehicle. So you can put a wind tunnel model like that in a hypersonic tunnel painted with this special paint, and you can take pictures of it and you can get that temperature distribution. Here's my little figure of aerodynamic forces. We had all sorts of data from both the flight data recorder and the telemetry that gave us a pretty good indication of the timeline. If any of you ever want to come into my office, I have this enormous poster. It's like 10 feet long, which basically shows the timeline of the shuttle reentry with all kinds of the individual data bits, you know, the temperature distributions and all the things that kind of we could fit on this great enormous poster. So that's kind of what we were trying to do. We looked at the debris. We looked at forensic analysis of the debris. Where was it ablated? What was its chemical composition? Did we see melted Inconol? I mean, you know, we saw all these things and we were able to figure out, well, we know what temperature Inconol melts at, so therefore the temperature on this particular piece was, I don't know what the temperature of Inconol is, but let me say 1200 degrees. It would be that kind of material, better than aluminum. So we had all sorts of stuff, and we analyzed it and put it all together for consistency. We did dissection of the foam. We analyzed this material. We analyzed it in several different ways. Microscopically, we found a lot of voids in the material. When the material, every time the material was flown on the shuttle, and this material is not you don't replace this material. This material is the same material that was used on the original shuttles. Every time it flies, it loses a little bit of stuff through vaporization, and so then they kind of try to paint it again. But I think our hypothesis is it just gets weaker and weaker as it's being used, and the problem is it's hardly being made anymore. It's material that was all made at the beginning of the program. It's not being made anymore. It's very expensive. So it's not a material that is easy to get. And in fact, that became an issue for us because one of the things I'll show is we wanted to do a full-scale mock-up of the leading edge, and we wanted to test it with a piece of foam going 800 feet per second. Now, why would we want to do that? Well, that's exactly the test conditions that we wanted to simulate. Well, that's not only expensive, but this material, it just doesn't exist. I don't remember where we got the material. We probably took it off of Endeavor or something like that. But I mean, this was a big deal that we should run this test because the material is very precious. But anyway, we banged on the table and said that we were going to do this and that they had to support us. We did the wind tunnel tests.
Question about that test. My reaction as an outsider when they published the pictures of the holes in that test was wow.
Wow, that was my reaction too. Yeah, my reaction was wow. And in fact, I was actually, one of the things we had I never had one before. We all had BlackBerries. And I never had a BlackBerry before, and I gave mine back to NASA and said I didn't need it. But I was actually at the Oakland Zoo with my grandchildren. And I got this thing on the BlackBerry that said that the test blew a 16-inch diameter hole in the leading edge. And I just said, wow. And I sent it back. It was really an amazing thing, and I've got the movies of that to show you. So anyway, we did the tests, and we studied timelines. We conducted arc-jet tests. We did forensic analysis of debris, both chemical and sort of physical. So we did a lot of different in-depth analysis. The test itself, in addition to being expensive and working with material that was really hard to pull together enough of this material to run the test, was also emotional. It was also an emotional event for the people involved. It was, and just very late in the game, NASA said, well, we are prepared to accept that the foam put a hole in the leading edge, so don't run the test. And we said, well, you may be prepared to accept this, but somewhere down in your organization is someone who doesn't believe that. And this test is for him. I actually met that guy. I mean, there are people in NASA who do not believe this. So maybe what makes sense is, let me show the movies and then we'll have our break. Okay, so let me see if I can get to. Okay, now here it is. Here's the wow. Can I hear it from the class? Wow, okay. No, I mean, and this really was, the guy who developed this material, and as I say, I have great respect for that material. It's almost state-of-the-art. But he cried. He was in the audience. When he saw this, he cried. It was such an emotional event to think that this material that had been the mainstay of the shuttle program, protecting the vehicle and the astronauts from these incredible temperatures, could in fact break apart. Let me do one more. Let me do it again. And then I'll show you one more from the inside, which is kind of a sort of gee whiz thing. Okay, so let me go inside. This is inside. Got a camera mounted inside. Wow. Yeah, that's kind of a gee whiz thing. Because you can see the deformation. You can see the deformation before it breaks. Let me see.
Was that in a wind tunnel?
No, this was a full-scale mock-up that was done at Southwest Research Institute. We had a big mock-up of the vehicle. It was done outside. Southwest Research has been involved in the shuttle program for quite a while. They have a foam gun that they have used to shoot foam primarily at the underbody tiles. The concern has always been on the strength of the tiles. You guys know what the tiles are? That sort of foam stuff that is underneath the vehicle. So they've done a lot of tests on foam, not big pieces of foam, but sort of small pieces of foam. Never tested the leading edge because it's damn expensive to test this leading edge material. And the only tests I'm aware of were these, BBs that were shot. Let me do this one more time. Oops, oh, come on. Where are you? There you are. So this is really the first time this test was done. Now, let me make a profound comment about space systems. There is a fundamental principle in the development of space systems. Test as you fly. You all know that. I hope you all know that. This test should have been done at the beginning of the shuttle program. It was not done. This test, and the reason it wasn't done is because there was a requirement in the shuttle program that foam shouldn't come off the orbiter, or off the whatever that thing is, the tank. It was a requirement that foam shouldn't come off the tank. So therefore, why do the test if it's a requirement that foam not come off? Well, the fact of the matter is foam has come off on every single shuttle flight, as far as we know. So this was a violation of the test as you fly principle. That is, I would say, the #1 principle in the development of space systems is test as you fly. It is the most important thing. Anyway, we can take our break now.
Yeah, and remember J.R. Thompson's remarks about testing to failure, which they did on the main engine,
Yep.
they didn't do on the SRBs, and they clearly didn't do here. Yeah. Okay, quick 2-minute, you know the drill.
Okay, let's see, before I leave this, I just want to, yeah, I just want to, this is not a very good day. I don't know if that's Texas time or Boston time, but anyway, it's 1:30. It was been outdoors. What you see is a sort of okay. What you see is a sort of an aluminum frame. I mean, what we have here is really what would be called a full-scale mock-up. It's an aluminum frame that holds the tile in the right position, and I suppose holds it with fittings of the right strength. In other words, what you're trying to do is replicate with what would be called a full-scale mock-up the structural conditions of the leading edge. So you'd have fittings holding the panels, and then you'd have it angled properly to the foam gun, which is over here someplace. And then, you fire the foam at 800 feet per second. So that's basically the test, and as I say, it was done outdoors, and it's quite spectacular. Big audience, there's a media, NASA, and big audience. It was quite an event. Okay, so as a result, that's not me. So as a result of this, the committee felt pretty confident that we had identified the technical cause of the accident. When we started this, we didn't know how sure would we be. So we had all these words like probably, more likely than not, conceivably, because we needed to think about describing our certainty with whether we knew, in fact, what had happened. But by the time we finished all of this, because everything had lined up so well, we felt pretty confident that we knew, in fact, what had happened. And so we all sat down around the table and argued about these words. This was a committee consensus. We voted on every word. Well, not every word. Some of the words are obvious. But, we basically came to consensus on every single important word in this statement of technical cause. So I'll just sort of let you read it, because it took us a long time to write. I should mention that one of the things, and I think this was from the flight data recorder, I really have not given you as much data about the flight data recorder, but one of the things we had from the flight data recorder is an indication of conditions on ascent relative to earlier flights. And if you look at the conditions on ascent, you can make a pretty good case that there was a hole in the leading edge on ascent, after the foam had hit. Because you see increased temperatures on the sensor right behind that region of the leading edge. And so you can make a pretty good case that the hole was there on ascent after Mach 2.5 or whatever the Mach number was.
But that was data from the data recorder?
I believe it was from the flight data recorder. So we didn't
get that on telemetry?
They did not have that from telemetry. Yeah. I'm pretty sure about that. But I'm not absolutely sure. Yes?
So what did the flight control team know about the foam being
Oh, they knew that weekend. Oh, in fact, I'm going to talk about that because that's part of the organizational and cultural issues. So finishing the technical cause. So this was our final statement about the cause of the accident, but we didn't stop there. Not this group of people, because this. Yes.
Oh, I was going to ask how soon did you arrive at the hypothesis that the hole led to the gases, led to the
I think pretty quickly.
Pretty quickly.
Yeah, I would say. Yeah, I would say it was pretty quickly. Now, there was a little pushback from NASA on that, but I described my appearance on February 18th on the board, and the fact that we had the wire cutting sensor information, that we had the video of the foam hitting the shuttle and exploding, and it was a shattering of the foam. And we had the aerodynamic forces, which indicated damage to the vehicle, which were consistent with a wing leading edge. We had the picture from Kirtland of some bulging around the wing leading edge. So I would say we had, I would think by, sort of this third week in February, that's where we were headed. Now, you don't want to get blindsided.
Yeah, were there any?
Oh, sure. No, we don't want to get blindsided. There wasn't, we got lots of inputs from the public as well as from the scientific community, and there was an input that we felt we had to take seriously, and I could sort of say what it was. We got an input from sort of solar physicists who said that on that day there was a violent sun episode that would have sent a shower of solar radiation to the Earth on that particular day, and that it's possible that this could have created some kind of shock wave in the vicinity of the shuttle and done some damage. So, I mean, it was a credible hypothesis. So, I called the Air Force. At Hanscom, we have these guys who do basically radiation physics, radiation weather, space weather, and Jim Halleck from DOT kind of shepherded that part of the project, but Jim is a physicist. He has a PhD from MIT. He works in the Department of Transportation, and so the two of us got together. We said we have to take this seriously. We have to put an expert team together and completely examine this hypothesis. So we did that. It turned out, and we had data from all over the world of this radiation coming in, and so it was very exhaustive. It turned out that this radiation didn't reach the Earth until 3 p.m. on that day, but we took it seriously. I think that was probably one of the most credible things. We obviously got a lot of junk stuff, that was an Israeli plot or something like that. I don't remember, can't even remember those things. But I think those are and then I think that, there was always this suggestion that it was just a micrometeorite, but I think because of the magnitude of the damage and the fact that the Air Force, I think this is general knowledge, the Air Force watches space junk. They have a catalog of everything that's flying up there, and there wasn't really a piece up there large enough to do that kind of damage. So that was eliminated. So there were a number of hypotheses, but again, when we did the data, we didn't go in with a hypothesis. We went in to see what the data told us. So, it was, that was a bit of independence with respect to the data and the analysis. Yes?
Did Shuttle wing broke because of damage of the leading edge.
Yes, eventually.
Creates this low and roll component.
Yes, yes,
that's how
exactly.
It rolled while it's
Yeah,
rolling,
exactly.
And so I was wondering, because this wing structure appears to be multiple spines, pretty strong structurally.
It's, well, depends on, yeah.
Was failure of the fuselage or overall breakdown
Yeah.
due to dynamic pressure, that was
No.
first, or what?
No, it's melting. No, the temperatures. See, it's aluminum.
No, but it was eventually entire system broke up because it
Eventually.
pressure, right?
Well, I think heat was the main culprit. You know, the dynamic pressures, and I'm sorry I didn't bring the graph. Dynamic pressures in this regime they weren't that large. I'm thinking they're less than 100 pounds per square foot. You know, because you're really up at very high altitude. And even though you're going very fast, the dynamic pressures are not that high. I actually have a graph of dynamic pressures. In fact, you come into my office and you'll see the dynamic pressure as a function. I would think that the way to think about it is that the important parts melted. See, we know from observations, and I didn't show all of these, but people were recording, I don't remember what we called them, but big pieces of the shuttle were coming off. You saw the video with all these pieces flying in, but we have pieces coming off as early as California. So, and I think we hypothesized at one point that the upper wing came off. In other words, the upper surface of the wing just lifted off. And the reason it did is not so much from pressure, is that all this gas is in there. Aluminum melts at, what, 700 degrees Fahrenheit or some ridiculously low number. We're talking 7,000 degrees Fahrenheit. So we're talking about destruction primarily by arc jet. You know, you have to think of the atmosphere as a big arc jet. You know, eventually the vehicle became uncontrollable, unflyable, because the aerodynamics were so off-nominal and the vehicle couldn't be controlled. But again, even, I think the dynamic pressures didn't get larger than 200 pounds per square foot, I don't think, which is about what I'm doing right here. It's about 200 pounds per square foot. Yes?
So what happened to the crew? Were they alive until impact?
I mean, yeah, I probably don't want to talk about that. We have some information about well, let me see what I can say. The vehicle itself stayed intact through a large part of the reentry and got into what would be called the fighter pilot's regime, you know, 50,000 feet. The actual cause of the death of the crew was what any fighter pilot would experience if he lost his vehicle at 50,000 feet. It's blunt force trauma. That's what it was. And we found a lot of the cockpit. We found, you know, reentry is really interesting. There's something called ballistic coefficient. Do you know about ballistic coefficient? We found briefcases, pillows, you know, anything that has a, well, ballistic coefficient is people talk about it in two different ways, and one's the reciprocal of the other. I always get confused about that. But if you have a low ballistic coefficient and you drop a pillow at, you know, Mach 25 and you know, 400,000 feet, it will probably make it to the Earth, because it'll slow down and then it'll just gradually float down to Earth. So we found a lot of the crew compartment, a lot of, you know, pillows, chairs, you know, all the stuff that was really light, just re-entered without burning up because of ballistic coefficient. So there was a lot there. Okay, so let me just see if there's anything else I want to say in this general area. Okay, now let's talk about the other part of our investigation, because this was the second shuttle accident. And we decided that we did not want to be report number 2 to be put on a shelf beside report number 1. That we were going to try to put everything together and make a report that, you know, would really try to solve some of the issues that NASA as an organization was facing. And so that gets into some of your questions having to do with when did they know, and you know, and of course the big why question. So let me go to that. Okay, so now I'm going to go off into the second part of our investigation, and we consider this to be as important, if not more important, than our technical investigation. So we talked a little bit about the history of the shuttle program, and I'm sure that's something that you have been through in terms of you know, the budgets, the margins, what we believe is a mischaracterization of the vehicle as a mature operational system. And so we think that there's a story here to be told, and so we looked into this. Now, I have to say that I was not as much a part of this as some other members because I was busy on the aerodynamics part of it. But you had John Logston, we had quite a number of the Air Force people, and Admiral Gaiman were more deeply involved in pulling together the sort of history of how this happened, the cultural issues. So I'm sort of reporting on behalf of my fellow board members what our conclusions were and the data that we gathered together to put this together. So the things that were pointed out is that there was this fundamental uncertainty in the shuttle program, and that led to a sort of fluctuating attitude towards investing in upgrades and infrastructure. The nation didn't really know where it was going. NASA, and I hope you won't take offense at this, but we found... You work for NASA. We found them to be an extremely insular organization. And I think actually they still are. They don't take advice from the outside. And I'll be prepared to admit that they are the only organization that does human spaceflight, at least in our nation. But they're not the only organization that handles risky technologies. And they have a lot to learn from other organizations. And they have not been a part of that conversation with people like the nuclear navy and some of the commercial industries that use extremely risky technologies. They've not been a part of that dialogue. And that's where we have criticized them. They, as I say, they are insular. They think that they can't learn anything from anybody else, that they know how to do all of these things, and that they don't need to accept any external suggestions. That's a very dangerous line of reasoning for an organization, and really no matter how good you are. So we felt that the people at NASA, the leadership clearly believed these things, and the people in the engineering workforce were under tremendous pressure to go along, in some sense, with these basic attitudes. And we saw that in our investigation of kind of what went on during the flight. I mentioned before that there is this history of foam, and let me introduce the word anomaly. Have you talked about anomaly?
Not directly.
Okay. Anomaly is one of the most important words in space systems. You know, anomaly means that something happened that shouldn't happen. Anomaly should bring your organization to a standstill while you figure out what happened and why it happened. Anomaly is a violation of requirements.
Sometimes I think it's a euphemism for failure.
Well, yeah, hopefully you catch it before failure. Anomaly is a clue that something may, even worse, happen down the road. It's something to be taken extremely seriously. The foam shedding off the tank was an anomaly. It didn't destroy the vehicle, but it is a violation of requirements. And in the early days, you know, it was really put on a list of problems to be worked. I mean, NASA didn't completely ignore it, but they put it on a list of the other 5,000 problems that needed to be worked. And they just kept flying until foam shedding really became a normal expectation, that all the flights would have foam shedding and that nothing serious would ever happen. It was treated as a maintenance turnaround problem. You know, when the vehicle gets back, we can fix it. And that was true in this case, too, that it was treated. They said something like, well, if foam hit the shuttle, we'll fix it when it gets back. I mean, that was the stance. Now, I think what's interesting about this, if you think about this, is that the anomaly of foam shedding without hurting the shuttle was treated as if it were a planned engineering test. In other words, if it was a test that was planned to see if foam could hurt the shuttle. And the fact that foam didn't hurt the shuttle was treated as confirmation that foam couldn't hurt the shuttle. Now, I think that's kind of fundamental. I like that particular phrase. There was enormous schedule pressure on NASA. They'd already slipped a couple times because of other, what I would call strong signals. We use the word strong signals. When something really dramatic is identified, NASA shuts down. Now, I don't remember the issues. There were, something about a connector that didn't seem to work properly, and it just grounded the shuttle fleet for 3 months or something. And there was some other problem that was a strong signal, and they simply shut it down. The foam, we put in the category of a weak signal. It's something that, while you're fighting all the strong signals, it's hard to justify shutting the organization down for what you perceive as a weak signal. So they had used up almost all of their margin to complete the space station, and they were under tremendous pressure. Sean O'Keefe was obviously sent to NASA to put the house in order, put the schedule and the budget in shape, and get the space station finished by February 19th of, we've already passed that one. Okay, so talk a little bit about what happened on the ground while the vehicle was in the air. I mentioned before that in the military we do 2 investigations. We do a safety investigation where the testimony is privileged, and we do a investigation which is public. And our group was kind of doing both. In other words, we were obviously doing a public investigation. We had press conferences every week, and the media would come and we'd share everything with them. But because we did have so many military people who understood the importance of accident investigation, we also had an annex, I guess you'd call it, of a way to take testimony and keep it privileged. And we did that. We took testimony from individual people at NASA. It was privileged testimony, and they felt free to share with us their participation and what happened and who said what when and all of that. Now, we had the damnedest trouble keeping this from Congress. I mean, it really was. And anything that's written down is accessible to Congress. At least that's the way they look at it. But we really held very firm, and we would not allow this privileged testimony to be accessed. And I think the compromise we made was that a staffer could come over to where we were located. They could read the testimony and take no notes. Well, they soon tired of that. So the fact of the matter is they didn't come. But we had a lot of privileged testimony that allowed us to put this picture together with employees not being too concerned about the implications of sharing with us. So the weekend that the flight went up, NASA knew that there was a potential problem, and they put in place something called a debris assessment team, which is supposed to look at all the data that they had and decide whether or not there was a problem. Now, I've chaired a lot of committees, not only here at MIT but other places, and I understand how important it is for a committee to have a clear charter and a clear line of reporting, and to have a certain level of independence from their home organization. For example, if I was chairing a committee here at MIT on an important research issue or important policy issue, and members of my committee were getting pressure from their department heads, I would blow the whistle. I would say that that's not the way a committee works. A committee has a charter, it has independence, it is not subject to outside influence from the people to whom these people report in their normal way of life. So with respect to the debris assessment team, I would make 2 comments. First of all, they had a very unclear charter. It wasn't clear kind of who they reported to or what their authority was. And they, as individuals, were getting pressure from their home organization, both NASA and the companies, the USA, Lockheed, Boeing, because those guys were getting pressure from NASA. So it's just an enormous amount of pressure being applied to various people in what I consider to be a totally inappropriate way. In any case, this team, and I admire them. I mean, I think they were trying to do a good job. They wanted to get on-orbit pictures to see whether or not using national assets, we could take pictures of the shuttle. And so who do you contact when you want something like that? You talk to the Air Force. And the Air Force, of course, is like a great collie dog, just waiting to show what they can do. You know, I mean, they just, oh, great, we got this wonderful opportunity to go take these pictures. It's really going to be fun. We're going to show what we can do. They're very enthusiastic about responding to that kind of request, but NASA didn't want the pictures. I mean, the senior managers of NASA didn't want the pictures. The debris assessment team did want the pictures, and they tried to make these requests of different parts of the organization, and every time they'd make a request, it would get slapped down by senior managers. There were, well, I guess we have it. This is a highly classified area, but let me just say there were 8 separate opportunities where we could have gotten some significant information about the state of the shuttle. And we didn't do it. We didn't do it because every time there was a flurry of activity around there, NASA said they didn't need it. They'd fix the shuttle when it got back. One of our recommendations was that, yes?
If the damage had been discovered on orbit, what do you think would have been done?
Well, I can talk to that issue. I mean, this is as good a time as any. We actually asked NASA to do some studies about what could have been done. You know, this is a nation that will save a whale that's trapped in the Arctic, you know, or a baby Jessica in the well. I mean, if we find that there is a crisis, we will mobilize. There's no question about it. It would be a very chancy situation. We know the vehicle is destroyed. The vehicle is lost. There's no question about that. The vehicle cannot re-enter safely with the people. So what was the best option? I mean, you know, we looked at the possibility of stuffing the hole with things, you know, old sleeping bags and suitcases and stuff, you know, and there wasn't anything on board that could have withstood the temperatures. And of course, one of our recommendations was that there should be some capability for in-flight repair. That's been a big issue. But the only other thing you could do is to sort of go into life support mode. Jettison the science, you know, stop doing the science. Jettison the module, I guess, which would make the vehicle lighter, and then maybe the reentry would be a little more successful. Conserve electricity, conserve water, conserve food. Try to stay in orbit for an additional, I don't remember the number, 15, 16 days, something like that, so that you could send up a second shuttle. I think Atlantis, they could get, I think it was Atlantis. They could get Atlantis ready, send it up. What?
It was sort of by chance,
yeah.
But it just happened.
But it could have been done.
In this mission, they did have the possibility of doing a rescue.
Right, so they could have, it's a gutsy move, but I have a feeling that if we actually had that information, that we could have put that together. It's interesting that when you read some of the stuff that's being talked about, like the Hubble and things like that, we did not recommend that a second shuttle be standing by. But that seems to have been internalized at NASA as a potential safety measure, that they will always want to have a second shuttle standing by if they send the shuttle up. The problem with that is it's a bit of a going out of business strategy because there aren't that many left. Yes?
Would a Soyuz capsule be able to or several of them?
We never looked at that option. We simply didn't. This particular vehicle was not in an orbit that could have reached the space station, and that's another big issue, is whether you want to have the space station available as a safe house if you have an accident. In this particular case, this vehicle could not have reached the space station.
Also, Soyuz could not have reached this because Soyuz launches from 51 degrees. This was in 28 degrees. Also, remember there were 7 people aboard.
Yeah, no.
So, you know, you would have needed 3 Soyuz.
Yeah.
The Russians just don't have them available.
Yeah.
So it was either Atlantis or nothing.
Yeah. Larry, you had a question.
Going back to the on-orbit photos, there was a legend at the time that the NASA management thought that the quality of the photos was what it had been several years earlier, and therefore would not have helped.
Yeah, let me speak to that, because I was going to mention that. One of our recommendations was, in the early days of the shuttle program, there was in fact a good interaction between NASA and the national security apparatus that does this sort of work. And people at NASA were cleared to an appropriate level to have this interaction. That has atrophied. The current people at NASA basically have no experience with that world, are not cleared to an appropriate level, have just not had an interaction, and see it as a bigger deal than it really is. It's not a big deal. We do it all the time. It's my collie dog friend, you know, I mean, it's just not a big deal. So our recommendation was that there should be a better interaction between NASA and the national security apparatus, and that the senior people at NASA should be cleared to an appropriate level to have that interaction, and that this should be, in fact, routine, that you always take pictures when the shuttle is in orbit. And so I think that was basically one of our recommendations. Okay, so in any case, we were not pleased with the decision or the failure to take photos of onboard. Maybe, I don't think I have a slide on this, but there was also the debris assessment team. Well, this is a bit of a comedy of errors. The debris assessment team was charged with trying to figure out whether this was a serious problem, and so they brought a tool to bear which was totally inappropriate for the task. It was called the crater model. Its fundamental purpose was to figure out whether foam would hurt the tiles. It was developed as a result of the experiments done at Southwest Research Institute of shooting small pieces of foam at the tiles. Not the leading edge, but the tiles. So they, and you know, it's sort of all things kind of rolling together. The people who developed this model were in Huntington Beach, California, when they transferred the operation to the Cape, or to Houston, I don't remember. The senior people in that group refused to move, so they turned the tool over to junior people. And so, you know, there was a loss of corporate memory, a loss of understanding, you know, so it just got worse and worse and worse. And so finally the people who were applying these tools were not the same people who were involved in the development of the tool, and really lacked understanding of what this tool was all about. The tool predicted that you had a serious problem, but they said, oh, well, the tool always overpredicts. So they ignored it. They said there's no problem. So, I mean, it was just cascading of kind of bad things happening. So we talked a little bit about the organization of NASA, and I don't know whether you talked to Aaron. This would be a good question to ask Aaron Cohen, setting him up here, about an independent safety organization at NASA. Yes?
How much did the crew know about all this?
As far as we can tell, nothing until about 1 or 2 minutes before.
Actually, the mission control had arranged for a press conference with the crew in orbit.
Right.
Are you going to mention that? Because, I mean, the crew knew that some foam had come off, but they were told that it was no problem.
Yeah. Yeah, but that's different than the crew knowing.
Right.
No, I think that is true, that the crew was notified that there had been an incident on liftoff, but there was no problem. Now,
the only reason they told them was because somebody from the press might ask them. And they
no, I've had media training, so I know exactly what they were thinking about. The shuttle lands, the astronauts get out, the microphone gets into the, you know, the mouth, and they say, "Do you know?" And the astronauts would say, "Of course, we knew. We understood it was no problem." So I mean, it was a pre-media sort of skull session for the astronauts, as opposed to a more responsible concern. What we do know about the astronauts is we have, you know, the voice recording and stuff, and I think there was something from mission control to the astronauts saying, we see a temperature anomaly in your wheel well. The temperature was 50 degrees higher than would have normally been. And this was, you know, literally just like, I don't think any more than 5 minutes before the vehicle lost control, maybe even less than that. I mean, it's all in the timeline. and that's probably all I want to say about it. I think the evidence we have seems to indicate that the astronauts knew that there was, obviously when the vehicle went out of control, they knew it was a problem when it began spinning and stuff like that. But as far as we know, there was no indication prior to that. Everything else was sort of nominal. Yes?
After both shuttle accidents, you have investigation boards, but
Yes.
what happened after Apollo 1, for example? Did NASA solve its own problems?
You know,
Is
I
that
don't
better or
know the
worse?
answer to that. I don't know the answer to
Well,
that.
actually, that's what Aaron did talk about, safety
Yeah.
organization
Yeah.
with respect to that and Apollo 13, and
Yeah.
the fact that when it was set up, they did start out with a very strong
Yeah.
independent
Right.
safety
Right.
organization, which did not exist before Apollo 1,
Yeah.
and the problem was the deterioration of
Yeah.
that, which I guess
Right.
you're going to say something
Well,
about.
I will say something about it. I mean, it is fairly obvious that one of our strong recommendations was that there be an independent safety organization, and that it not be a weak organization reporting to the program manager, that it be an independent organization that is basically in charge of requirements, in charge of I guess the final word on mission readiness reviews or whatever they call those things. Now, why did we say that? Well, you're all engineers. The idea behind an independent safety organization is that you should have engineers fighting. So how do engineers fight in an ideal world? They fight with data and analysis and hypothesis and testing and, in other words, if the program wants to waive a requirement, change a requirement, then they have to present a case. And if the safety organization feels that there's, crossing the line, then they present a case. And the two organizations basically try to bring together the best analytical and experimental framework they can in order to determine what should be done. And so that's the notion of an independent safety organization. I guess the thing that I was somewhat gratified by, we'll see how it all works out, is that we recommended as a return to flight thing that NASA present a plan for an independent safety organization with the idea that in the midterm they would actually begin such an organization. Sean O'Keefe took that he took the bit in his teeth, I guess is the way to say it, and he moved out much more strongly on that than I would have anticipated. We met with him last December, I guess it was December, these years go by very quickly, but he had actually put in place a structure to get ready for the flight that had outside experts from within NASA, but to sort of come together as a independent safety board to look at anomaly resolution. I guess he didn't do too good on the foam. But in any case, as far as the structure goes, it was a stronger safety structure than had existed before. So that was something that we recommended, that it was very important that there be an independence in the safety organization, and that this is in fact a characteristic of an organization that effectively manages high risk. And we would claim that there are several such organizations in our country, and there's a lot to be learned and a lot to be shared. So we also looked at the comparisons between this accident and the Challenger accident, and in fact found more similarity than you might have expected. Given that Challenger occurred on liftoff and this occurred, well, in reentry, but actually did occur on liftoff. In terms of the role of engineers and technical managers, this notion of normalizing deviance. Deviance is an anomaly. It's a departure from the requirements. And if you normalize it, it means you accept it. You accept it, and in fact, you try to profit from it by saying that it's proven that that there's no danger. So this phrase, normalization of deviance, is an important sort of technical phrase that our group used. We had with us actually a faculty member from Boston College who had written a book on the Challenger investigation. She's a social scientist, and she worked very closely with us to try to put what I would call the social science and organizational effects together. That's Diane Vaughn. You might bring her over sometime. fascinating speaker. Yeah. But the thing that was interesting about Diane, not only was she a great colleague, but she said, that she published her first book on the Challenger accident. And it's an in-depth analysis of the cultural flaws in the organization that led to the Challenger accident. So she published this book, and she said, well, I got a lot of reaction from the book. She said the Navy called, my old boyfriend called, the various industries called to have her come and talk about safety culture. NASA never called. NASA never indicated any interest in her analysis of the cultural flaws within the organization that led to the Challenger accident, which I think is another indication of the insularity. So that was, I think, an important input to our look at the organizational issues. So we got together, and as a result of all of this, and as I said, I wasn't deeply involved in, say, some of the privileged interviews having to do with the individuals, but certainly as a board, we came to this organizational cause, which we consider to be as important as the technical cause. And the various words, rooted in Space Shuttle's program history and culture, original compromises that were required to gain approval, the years of resource constraints, the fluctuating priorities, the schedule pressures, the mischaracterization of the shuttle as operational rather than developmental, a lack of agreed national vision for human spaceflight, the cultural traits and organizational practices that were detrimental to safety that we're allowed to develop, including reliance on past success as a substitute for sound engineering practices, such as testing to understand why systems were not performing in accordance with requirements, organizational barriers that prevented effective communication of safety information and stifled professional differences of opinion, lack of integrated management across program elements, and the evolution of an informal chain of command and decision-making process that operated outside the organizational rules, a bit of an old boy network in some sense.
And we should mention that lack of agreement, of an agreed national vision for human spaceflight has been the jumping off point for everything that has happened since with the new vision, which is presumably going to determine what we do in the next 10 years.
Yes.
So I think it's great that all of you called attention to that.
So let me talk about our recommendations. We made recommendations in basically three piles. One of them are the near-term recommendations, which are the return to flight recommendations. And these were monitored by a committee of 28 people. That's enormous. In any case, we asked them to present a plan for an independent safety organization. I think they went a little further. We asked that they develop a method to do onboard repair. Now, there was big discussion about onboard repair. It's very clear that it is much easier to do onboard repair for all sorts of different reasons, including crew safety, if you are going to the space shuttle. Station. If you're going to the space station, because then you've got a safe house and all sorts of supplies. It's like your recreation room. If you're not going to the space station, it's considerably more dangerous, and that is the fundamental issue with respect to a Hubble mission, because a Hubble mission is incompatible with going to the space station. So if you take this recommendation seriously, you either have to develop an autonomous onboard repair, which is much more difficult than a space station onboard repair, or you can't have any Hubble mission. So this is a bit of turmoil in the political issues surrounding missions. The other impacts, as I mentioned, it's not our recommendation, but this notion of having a second shuttle standing by seems to have been internalized. There were a number of other recommendations. Our report's on the web. I mean, more video cameras, more onboard video that gets telemetered to the ground, during the flight, so you don't have to wait till the vehicle gets back to see the video. External video cameras, launch during day, keep your sensors up to date. I mean, there was just a whole lot of, I think, 25 recommendations of a return to flight. And the Return to Flight Committee was in charge of monitoring all of those, and they've recently issued a report. Incidentally, I got a copy of the Return to Flight report, and I donated it to the Aero Library. So it should be in the Aero Library. And there was a very interesting minority report that was submitted by like about 5 people, which was just damning with respect to their observations about how NASA works the safety issues. So I mean, you know, take it as the opinion of these 5 people who were on the Return to Flight Committee, and you know, it makes good reading. But that's all in the Aero Library. Okay, now our midterm recommendations were, you know, in some sense, we made these recommendations assuming the shuttle program would continue, and I think we had this recommendation for an independent safety organization, and what I thought was one of our most important recommendations was that if you intend to recertify the shuttle past 2010, if you intend to fly the shuttle past 2010, you should recertify it. Now, certification is a very technical process where you have to go through every piece of equipment and, in some sense, revalidate that it will satisfy the requirements and retest it, and you know, it's a big project. But if you want to change the culture of an organization, or if you want to get 2 organizations working together, the best way to do that is to give them a project that they have to work together on in order to solidify their working relations. What better project for the Shuttle Program Office and the Independent Safety Organization than to recertify the shuttle? At least that was my vision. That would really be an extremely useful thing to do, to work together to recertify the shuttle. Now, unfortunately, evidently, the shuttle is not going to operate past 2010. So we'll see. I mean, so they won't recertify it. Now, I think what's going to happen is they're going to get up to 2009 and they're going to say, oh my gosh, we don't have any way to get to space. So there's going to be enormous pressure to keep the shuttle operating past 2010. And of course, they'll be late to need in terms of recertifying. So it's going to be a bit of a jump ball at that point. Should be very interesting to watch. Now, the long-term recommendation, of course, we made was that we need an agreed-upon vision for future manned spaceflight. And so from my point of view is we skipped the midterm. And we went immediately to the long-term, because with the President's new program that we have basically set this vision, and unfortunately we've skipped some of the intermediate steps that would have strengthened NASA as an organization in its ability to carry out a new mission. So I stand back watching as all of this develops, having had this incredible background of being a member of this Accident Investigation Board. That looks like I landed the plane right on time. Yes? Incidentally, I brought this Halloween candy, and I would really appreciate it if you guys would come and take it, because it's not something that my husband and I...
If it doesn't get eaten, would somebody please take it down and put it on the...
With graduate students. Yeah, good. Anyway, you had a question.
I'm wondering if you think there might have been any effect on that if it was explicitly stated that this is why we want the recertification to happen.
Oh, I don't know. You know, it's hard to micromanage. It's hard to micromanage a big organization. I personally was disappointed because I believe very strongly in this, and I felt that it would be a way to bring the organization together around this set of ideas. So that won't happen, and we'll see, you know, how they work with this, quote, independent safety board that they've put in place. And, you know, all of what we're doing is a self-education. It's organizational education, it's self-education, it's process education. So we'll see how they bring it all together.
Yeah, the reason I asked that was because I actually, like, in terms of reading, here's this recommendation, I read it a little different.
Sure.
I thought it was kind of a push to move past the shuttle. You know, to say recertification is going to be too complicated, so obviously we can't.
There might have been a little bit of that. I mean, it really was up to NASA to decide whether a process that was so resource intensive was worth doing. I mean, given the fact that the shuttle is in the sort of sunset of its career. So I guess I felt that we should leave that to them, but that they could not continue to operate the way they were operating. I think that was really the message. They had to make a decision.
Your board's recommendation of the number of 2010
Yeah.
has had enormous
I know.
impact.
Of course it has.
Very negative from my point of view.
Yeah.
Say something about how you picked that number and how flexible it is.
Well, you know, recall we did this in, what, 2004? You know, so we wanted to give NASA enough time to get back to flying. And of course, you know, the whole definition of what recertification means is a bit unclear. In other words, I would think that NASA could have gone in, you know, I think what we saw is, okay, we needed to get a couple of flights under our belt. But we needed to go back. What I think we meant by recertification is a relook at the whole mission, what's that thing called? Mission... No, not mission rules. When they get together and decide whether they're going to fly. Mission readiness review. So, yeah, flight readiness review. So we felt that the flight readiness review was broken. And that part of the reason it was broken is that there were too many requirements that were silly. Like the shuttle had only 2 wings instead of 4. You know, because you need redundancy. Wings are important, and if you really thought they were important, you'd have 4 instead of 2. And every time they did a flight readiness review, you'd have to go through these, what I would call silly requirements. So one issue about recertification was to try to narrow down to what were the key systems that needed re-examination in the light of technology and what we know about the shuttle. So that in itself would have been a very useful process that would have helped this. And so I think what we saw is that there is a set of processes that need to be carried out after a couple of successful flights that would really position the organization to do its job. And I think 2010 was a reasonable window for that.
Yeah, the consequence of 2010, from my point of view, is that it has forced the current administrator to say, well, to avoid a gap in launch capabilities, we have to hurry up and accelerate the CEV in order to pay for that. We have to drop science missions and so on. And it's cascading to what, in my opinion, is a terribly bad decision for NASA's future.
Well,
you know,
maybe they didn't start early enough. Maybe they didn't start early enough. They wasted a lot of time.
Well, but suppose someone had come back to you or members of the board and said, well, life would be easier for us if we called it 2013.
Well, I would think if you're going to do that, that NASA should come forward with a plan at the minimum of how they're going to operate the shuttle safely through 2013. They have not even thought about doing that. They're carrying on with business as usual, you know, flight, and they're not thinking about this more fundamental issue, which would, I think, be very useful for them as an organization of what are the critical issues if we wanted to operate the shuttle to 2013? They just kind of got off the hook by saying, 2010, we can do that. You know, it's pretty shallow. Yes?
And this is going to have to be the last question, unfortunately.
Anyway, you're all invited to my office to see my big poster on the flight.
Your recommendation for not flying unless you have a safe house in orbit.
No, we didn't recommend. Oh, a safe house in orbit. Yeah, okay. Yeah.
That surely would have cut out. If you had said that at the beginning of the shuttle program, that would have cut out dozens of flights.
Sure. But you see, at the beginning of the program, NASA was committed to a system that met its requirements. And once they backed off of a system that met its requirements, they left itself open to operating a risky system. And so then you come in after having 2 accidents and say, okay, how can we operate this system safely? You've already demonstrated that you're willing to back off on requirements. So how can we identify what some key issues are so that you get back to operating safely? So, you know, we fundamentally what we fundamentally recommended was that you should develop onboard repair capability, and that's really all we said. And we sort of left open how they would do that, and that, you know, they investigated a lot of things and decided that it would be a heck of a lot easier if they could use the space station for repair. And so they themselves said, okay, space station only. So that really was not our recommendation, although we understood that it would be a lot easier to do space station repair. Okay.
Thank you very much.
Okay.